If you are considering studying physics or engineering at university, then this is what I think you should do to prepare. So my name is Lewis from Physics Online, and although I make videos about physics, I actually studied engineering at university. I did a master's in mechanical engineering, had a great time there, I learnt a lot, and then I applied it in the first job I had out of university, where I worked for an engineering consultancy. Of course, I've also got a bit of experience in helping students prepare for A-level physics and therefore prepare for STEM subjects once they finish their A-levels. Now, I'd say that the most important thing you need to be doing to prepare for physics or engineering at university is to make sure that you're doing A-level physics and A-level maths, or some kind of equivalent. So it could be an IB, it could be pre-U, it could be international A-levels. Whatever it is, there needs to be lots of maths in there because that's going to be so important as you go into university. Now, the third kind of subject that you choose could be something like A-level chemistry, and that could really help you if you're doing maybe materials engineering or materials science. You could be doing something like further maths, which again will really develop your math skills. Although by the time you get to university, because everybody's come from such different backgrounds, from different places around the UK and around the world, they often teach the maths that they need you to know when you're at university. So further maths is great, but I don't always think it's essential. Of course, like anything, if there's a course that you want to do, make sure you have a look at the entry requirements and see exactly which subjects they want you to be doing. Now, of course, you don't have to be doing chemistry or further maths. You might choose something like biology. For example, if you want to go and do medical physics in the future, then obviously you need to understand the physics, but having a good understanding of the human body and organs and things like that, that can really help you. And it's really interesting. And again, it's a science, and therefore it leaves you with plenty of options if you decide to change your mind in the future. But of course, you could be doing something like economics, you could be doing another language. As long as you've got maths and physics, that's the most important thing that you're going to be relying on. Now, when you're at school and you're learning the content, it's important to listen to what the teachers are telling you, to make sure you do the minimum work that they're setting, like the bits of homework and the bits of classwork. There are other resources, of course, that you can use to help supplement what your teachers are delivering. For example, I've got a couple of videos where I explain a few things about A-level physics. There are other things like this workbook, for example. This one's a daily workout, and this has questions for every single day of the course. So that's the kind of thing that you could be doing, but everybody's going to be doing that anyway, because that's just doing your normal A-levels. The things that you might consider, in addition to what you're going to be doing in class, is maybe looking at Isaac Physics and answering some of the questions there, and also maybe thinking about competitions like the British Physics Olympiad. This has much higher level questions, which although they're based on your knowledge from A-level, they're set in a way that really get you thinking. So if you're doing those higher level questions, that's going to not only prepare you for any exams, which you have at the end of the course, like your normal A-levels, but it's also going to help you prepare for any university assessments that you might have. For example, if you're doing the PAT test, if you're applying to Oxford. So by doing this higher, harder level questioning, that's going to really help you. But the thing I really want to show you in this video that I think you can work through completely independently, and you could be doing this during your A-levels or even afterwards before you go to university, is this book here, actually also by Isaac Physics. Now, this is not a sponsored video. Unfortunately, I'm not being paid anything to say this, but I think that this is a super powerful thing that if more students knew about it, they would be better prepared when they start university. Now, this is a book that you can buy, and I think it costs about £1 from the Isaac Physics website, plus postage and packing, or you can actually access all of this material completely for free just by going to the Isaac Physics website. And what it has is well, it's just loads of physics really, but it's going to really develop your math skills as well. And it links different parts of the course together. So you can see that there are a huge amount of questions across all areas of physics. And a lot of this is going to be going beyond the course specification. And it's really aimed at the higher achieving or higher attaining or more motivated students like yourself, who are maybe wanting to go for the higher grades and therefore think about doing a STEM subject at university. Now, in a break with normal Isaac Physics tradition, they've even given you answers, but only to the first question. Something that is a bit of a limitation for some students is that on the website you can't find what the correct answer is. In the back of this book, it actually has all of the answers to the first part of the question. And some of them do look quite complicated, but it's nothing that you can't do if you set your mind to it. And if you're wanting to go and study at a high level in the future, you need to get used to working independently and actually trying to find the correct answer, even if it's not obvious. Okay, also important to have a nice cup of milky tea to help you study. What I thought I'd do though, in this video for the rest of it, is really show you one example of how you can actually work through this yourself. Now, Isaac Physics don't like to have people putting solutions out there, so I hope they're okay with this. But I think for this one, it's just a really nice thing to show you. So what we're going to look at is, well, we're basically going to start at the very beginning, and we're going to look at gravitational potential and kinetic energy. So this is something you will know about from GCSE. You will cover it at the start of year 12, but this goes slightly beyond the way you'd maybe be asked questions about this in any exam, and that's because there isn't a time limit. And this book has been put together by a great group of people. They know a huge amount about physics, and again, this is run through the University of Cambridge, so they definitely know what they're doing there. Now, you can, of course, do it in the book, but like I said, on the website, you can access everything. And to do that, what you need to do is go to the Isaac Physics website. You then need to select Learn, and you just choose their A-level resources. And you'll see on the right-hand side here, it says the Linking Concepts book. Obviously, this allows you to then buy the book if you want to. And we're going to start with Mechanics, which is Chapter 1, and we're going to view the board. Now, there are notes in here, which are the same as the notes in the book. So you can just read these. Oh, here we go. So it's got some information there, and they're saying, for example, that h0 is the starting height and h1 is the final height, and so on. So they've got their particular symbols they're using. Again, doesn't matter which exam board you're doing, the physics is going to be exactly the same. They've also got examples there and answers. So this is everything that you find in the book. Now, the first question here, it has these quantities, it has the equation, and the speed v1 at the ground if an object was dropped from height h0. Okay, so that's the first question. Now for this, I've actually put something together that you might find useful as you're actually maybe having a look at this book and deciding if it's a thing that you should be doing. I do think you should do this. It's going to really help you, like I've already said. And so what I've done is I actually basically copy and pasted onto this document that you can find beneath the video just down here. So you can actually download basically a blank version that has the same thing in the book, just kind of made into more of a worksheet, and you can write your answers in here. And of course, because this is what I do, I make resources to help you students. I've also got a set of my worked solutions where I go through this step by step. So if there's anything in this video that doesn't really make sense, then you can always download this and just work through it and then have a look at my solutions to see how I approach that same problem. And also, although I am of course pretty good at physics, I mean this is now my full-time job, I still made mistakes and I thought, oh, what have I done? And then I looked back at my working, I'd made a little silly mistake, and yeah, you don't always get it 100% correct the first time, but that is completely normal, even for experts like me. And of course, to check your answers, all you need to do is actually type them in to the Isaac Physics website, and it'll let you know if you've got the correct answer. So you can basically self-mark, you can record your stuff, and if you do this, I guarantee that not only will you get a better grade when you do your A-level physics exams, but you'll be much better prepared for the style of work that you're going to be going into as you go into university. University, they don't care if you don't go to the lecture. If you don't hand in your homework, nobody's going to be really looking after you like that. So you've got to make sure that you develop these independent learning skills. And if you can do that right in the first year, then the rest of the university kind of course that you're going through is going to be really, really straightforward. Let's begin in the time-honoured fashion with question 1.1 part A. So we have an object which is dropped from height h0, and it's going to reach a velocity v1 as it hits the ground. Okay, so fairly standard. If we know that initially it was up high, we can therefore maybe consider its store of gravitational potential energy. And in this case, that's going to be equal to mgh0. Okay, the change in height is the difference between ground level and the height it started at. Now, as that's falling, that's going to be transferred into the kinetic energy store, and therefore that we can say that this is then equal to a half mv1 squared. Okay, so nothing outrageous there. You might have seen that or used that many, many times already. Now, of course, we can see that whatever the mass of this object is, it's the same on the left and the right of that equation, and therefore those cancel. And therefore we could write this again as, let me just swap the pens again, we can say that gh0 is equal to V1 squared divided by 2. Okay, apologies if you are colourblind. I've just used a bit of colour to really help. It's not essential, but I've got green on that side and red on that side. But I'm using plenty of other colours, so you can still, even if you're not sure about the difference between these two colours, you can still hopefully follow my method. Okay, we can then rewrite this because we want to write an equation for V1. Okay, so if we say that V1, this is equal to 2 times GH, GH naught, and then we're going to take the square root of that. Okay, so that is the answer that we're going for. Right, the next one, we want to find the speed V1 at a height h1 if an object had speed V0 at h0. Okay, now the physics isn't that difficult. The complicated part of this is just trying to understand what the question is asking. So maybe let's consider the initial total energy of that object, which is going to be equal to its potential and kinetic energies, and also compare that to the final potential and kinetic energies of that object. It's harder to say than actually to do the physics. So first of all, let's go for green for this. Initially, it will have that initial gravitational potential energy at h0, and it's travelling at v0. Okay, and then it will have this energy at position 2. Now again, just like last time, we can see there's an m in each of these, so they all cancel out. And the next thing I'm going to do is just multiply both sides by 2 to get rid of the halves that we have under here, to say that 2gh0 plus v0 squared is equal to 2gh1 plus v1 squared. Okay, again, you can just see all I did here was I divided everything by m, so let's divide by m, and then I've multiplied by 2. But we want to, again, know the speed v1, and therefore we can rearrange this to make v1 the subject, and we do that by taking this off both sides, square rooting that, to say that v1 is equal to v0 squared plus 2g h0 minus h1, and then it's the square root of all of that. And I think that's probably the neatest way to actually represent that. So what I did was I had 2gh0 minus 2gh1, and therefore the 2g is constant, put that in brackets. Again, hopefully if you're thinking about doing physics at uni, you can follow that. The next one, we want to know the greatest height for an object projected up from the ground with speed v0. Well, effectively we've got exactly the same as we had up here, but now what we might say is that initially its kinetic energy was a half m v0 squared, and that's going to be the same as its final gravitational potential energy, which is mgh1. Again, of course, we have m's that cancel. That happens quite a lot. We want to know the value of h1, and therefore, if we were to maybe just write this out again, we could say that v0 squared over 2 is equal to gh1, and therefore that means that h1 is equal to v0 squared divided by 2g. Okay, hopefully that's making sense so far. Right, on to the second page of my questions, or question D if you are using the book or you're online. So we've basically done A, B and C, and yeah, we're just going to continue that for the next few. So again, this might be a bit of a long video, but obviously you can skip forward to the question that you really need a bit of help with. So now we want to look at the greatest height h1 for an object projected up from a height h0 with a speed v0. So initially it's had a gravitational potential energy of mgh0. We're going to add that to the initial kinetic energy, a half m v0 squared, and that's going to be equal to the final gravitational potential energy h1 at the highest height, where the velocity is going to be 0. Again, like we've done, and this is the thing, it might be at times repetitive, but you need to be doing repetitive things again and again and again. Just like if you go to the gym, you do the same thing again and again, and that's going to make you stronger at that activity. So again, we've cancelled the m's. I'm just going to write this out then as gh1, so I just put this over there, is equal to gh0 plus v0 squared over 2. And then we want to make h1 on its own, so if we divide both sides by g, what we find is that H1 is equal to H0 plus V0 squared over 2G. Okay, hopefully that's all good. Then we want to look at the greatest height H1 above a hard surface reached by an object dropped from a height H0 if the efficiency of the bounce is this letter in here. So this is actually the Greek letter eta. It's the one that we tend to use for efficiency, although exam boards often just have it written out as efficiency. So if you're not sure of anything, just Google it, or I guess use some kind of AI, and that will tell you what these symbols actually mean. Okay, so we've got something dropped from a height h0. It bounces, and it bounces up to a lower height h1. So we've got the initial energy, and then we've got the final gravitational potential energy. So let's think, if we had something which was ideal, then we can say that mgh0 would be equal to its final energy, which would be equal to mgh1. Okay, so that is something where we have something which is 100% efficient. However, h1 is going to be less than h0. It's not going to bounce as high, and therefore this symbol eta is going to go in front of this. Okay, so imagine the efficiency was 60% or 0.6. You'd multiply the initial height by 0.6 to get the final height. And of course here, again, you can see that we've got m's that cancel, and now we've got a g that cancels as well. And therefore, if we want to, I'm just going to write it out one more time actually, we can say that eta is equal, so eta h0 is equal to h1, and therefore h1, the greatest height, is going to be equal to eta h0. Okay, I'll just put that the other way around. Okay, so there's that one there. So now we've got an efficiency, which again is something we don't always have in A-level style questions. Now then we want to look at the speed v1 just after a bounce from a hard surface if the speed just before was v0, if the efficiency of the bounce is eta again. So we can do the same kind of thing. We can say that initially it had kinetic energy. We're going to, in an ideal situation, that would be equal to the kinetic energy afterwards, a half mv1 squared. But again, we're going to multiply this side on the left by eta. And again, of course, we've got m's cancelling for like the 6th time. The halves cancel. And therefore, we could say that eta v0 squared is equal to v1 squared. But we want to find in the question v1. So if we rearrange this, we can say that v1 is equal to eta v0 squared, and then we square root all of that. That's one way you can give the answer. That does look a little bit messy, so we can also write it as the square root of eta times v0. Okay, hopefully that's good. Right, so those questions over there, they are very much to warm you up, and all of those answers, if you're not sure about anything, you can just look in the back of the book. So if you do have the ability to buy a book and have a copy, I think this is incredibly useful. So let's have a look what it says. Yeah, so it's got the written things out there. It's got all of this. So that's exactly what we've just done. For the next few questions, I'm going to make a controversial move away from the Isaac Physics official colours, and we're going to have to use a bit of orange. That's just because I had an orange tennis ball. And also, the first question is about a pumpkin. So we've got an 800 kilogram pumpkin, falls 3.4 metres. Calculate its speed just before hitting the ground. Okay, so this one here, thinking about that conservation of energy. And for this, we've actually already written down the equation from part 1.1a. So the first thing I'm going to do is just write down the equation, even though nobody's going to mark my work. And if you're doing this, it's often quite tempting to think, well, I can just do the answers online. I can take a shortcut. It is so much better to write down the equation, to draw a diagram if needed, and that means you're far less likely to make a mistake later on. So normal things apply. So V1 is going to be equal to 2 multiplied by 9.81, normal value of G. It falls 3.4 metres from H0 down to the final thing, so that's just multiplied by 3.4. I'm going to take the square root of all of that. I find it quite hard to do these straight lines down here. And that means V1 is equal to, let me just work this out, equal to 8.167496556. But of course, if you've done any Isaac physics, they're quite strict on significant figures. I would say that 3.4 meters is two significant figures. So I'm going to give my final answer V1 as 8.2 meters per second. And that means when you're entering this online, just to check that, you need to make sure you use an appropriate number of significant figures and also put in an appropriate set of units as well. So question 1.2, yeah, a fairly nice beginning, I think. The next one, a 60-gram tennis ball is hit upwards at 27 meters per second. How high will it rise up? Well, for this one, what we can use is the equation that we worked out here. So this one here is from 1.1c. So we're going to use h1 is equal to v0 squared over 2g. And that's going to be equal to 27 squared divided by 2 times 9.81. And then when you do the calculation, this gives an answer of 37.16. So that's about 37 meters high. So that was my approach to that. Again, nice straightforward questions just to ease you up and warm you up into it. We now have a 60-gram tennis ball hit upwards at 27 meters per second from a 25-meter high rooftop. How fast will it be travelling when it passes the rooftop on its way back down? So now we can actually use the equation that we wrote down for 1.1b. So we know the heights, we know how quickly it was initially moving, we can work out V1. So I'm just going to write then that V1 is equal to V0 squared plus 2g h0 minus h1, and we're going to take the square root of all of that. Okay. Now, of course, what you might realise is that although we might have 27 squared, we've then got plus 2 times 9.81 times, and then we've got h0 is 25, and on the way back down, it's going to be h0 is 25, h1 is 25, and obviously we square root all of that. But you can see quite clearly that 25 minus 25 is 0, and therefore V1 is just going to be equal to the square root of 27 squared plus 0, which is then just equal to 27. And obviously the units are meters per second. Now, to be honest, I probably didn't need to write any of that down, because whatever speed it goes up at, it's going to be going at the same speed on the return journey at the same height. So that one there is kind of not needed. You didn't need to write all of that down. But effectively, if this went up at 30 meters per second, it would be coming down at 30 meters per second as it passed that point at h equals 0. Okay, we now have, I don't have a real brick for this, but we've just got a Lego brick. I think when I was preparing this, I realised I have so much Lego, I can find pretty much anything to kind of bring the question to life. So we've got some workers, bottles, pumpkins, bricks. Yeah, I think Lego's kind of taken over a little bit. Okay, so for this one, we've got a 3.1 kilogram brick, falls from some scaffolding on a building site. A worker 3.5 metres above the ground sees it fall past at 6.5 metres per second. What is its kinetic energy just before striking the ground? So, what we might think about is two positions. We've got the brick up here, and then we've got the brick as it hits ground level. So this is going to be, 3.5 metres from here to here. They see it fall past at 6.5 metres per second. What's its kinetic energy just before striking the ground? Okay, so that's my diagram. That's all I've done. That's kind of what I know from the question. So at this point here, the kinetic energy after is going to be equal to the kinetic energy before plus its store of gravitational potential energy before as well. Okay, and again, a lot of this notation here is actually given to you in the question. So you might be using PE or GPE or EP. I'm just going to use the way that they've got it here. So they've got EGP, they've got ET, ET after, and so on like that. So I'm using the same notation as in the book. And if you understand the physics, it doesn't really matter which one you use as long as it's correct physics. So we want to know the kinetic energy afterwards, and that's going to be equal to the kinetic energy before. which is a half m v naught squared. And so this is going to be v naught. We're going to add that to mg h naught. Okay, we can now put in some numbers. So ek after is going to be equal to a half times the mass of the brick of 3.1 multiplied by 6.5 squared. And we're going to add that to 3.1 times 9.81 times 3.5, because this height here is equal to h naught. And again, when you use your calculator, you'll find that the kinetic energy afterwards is equal to 171.926. I'm going to say to two significant figures like this here, that's the same as 170 joules, or I guess even better than that would be 1.7 times 10 to the 2 joules. Okay, so that's the answer for that one there. And again, if you're not sure, always draw a diagram, write down everything that you know, kind of label things, underline things. It's really up to you to kind of put that line of text into a logical kind of physics format. The next question was actually quite hard to prepare for in terms of trying to find like an orange Lego potter's wheel. So here's my wheel that would be rotating. This is going to be the initial lump of clay, and that's going to get thrown onto the top from a certain height. And then a very short time later, a pot has been formed. Okay, so let's think about what's going on. So we can actually use the equation. Again, this is from part 1.1b, and that's why they give you the equations or the formula to work out at the very beginning. We want to know how quickly it's going to hit it. So V1 is going to be equal to V naught squared plus 2g times h naught minus h1. Okay, and it's the square root of all of that. Okay, we can put the numbers in. So this is going to be equal to its initial speed because it's thrown down at 1.1. So that's 1.1 squared plus 2 times g, which is 9.81, multiplied by the difference in height, which is going to be equal to 0.40 meters. Okay, and when you work that out, we find that the final speed it actually hits it is 3.010, so that's equal to 3.0 meters per second. Okay, in actual fact here, although the mass of that clay was 4.2 kilograms, that wasn't needed to actually answer this question. Right, for question 1.7, we've got a worker at ground level. They throw a dangerous 2.2 kilogram bottle upwards to the worker up at a higher level. Okay, so a lot here. It just reaches him, but he fails to catch it, and it falls into an evacuated trench 1.6 meters below ground level. Now, I started this by drawing a diagram. We've got ground level here. H naught is 1.0 because she threw it to him from waist height, which was 1.0 meters. He was, his hands were 3.2 meters above the ground. So what speed did the worker need to throw the bottle if she threw it from the waist 1 meter above the ground? Well, what we can say is that mgh naught, the initial gravitational potential energy, plus a half mv naught squared, the initial kinetic energy, is going to be equal to the final gravitational potential energy of the bottle as it gets to the highest point, because at that point it's not moving, so there's no kinetic energy there. Of course, m's cancel, as we find all the time. We want to find v naught, and so if you rearrange this, we can say that v naught is equal to 2g h1 minus h naught, and the square root of all of that. That's equal then to 2 times 9.81 multiplied by the difference in height, which is going to be equal to 3.2 minus 1.0 square rooted, and that's then equal, because I did the calculation earlier, to 6.570, which is 6.6 meters per second. Okay, so that's how quickly she needs to throw the bottle just to get to the worker for the initial bit. But then how fast was it moving as it struck the base of the trench? So that it falls from here, past her, and then 1.6 meters further beneath that. So what I'm going to put up here is H1, which is 3.2 meters above ground level, and then it's going to fall a further 1.6 metres, but I'm going to call that minus 1.6 down to this final height of h2. So it falls from him, past her, down to the very bottom of that trench. How fast was it moving? Well, we can say that mgh1 is equal to mgh2 plus a half mv2 squared. We want to find v2, so v2 is going to be equal to 2g h1 minus h2. Okay, so I just rearrange this. So that's the initial energy, which was all gravitational potential, and then we've got some gravitational potential and kinetic finally at this point down here. So V2 is going to be equal to 2 times 9.81 multiplied by h1, which is 3.2. We're going to take away this distance, which is minus 1.6. So the total change in height is going to be 4.8 metres, square rooted, and that gives V2 as 9.704, which is 9.7 metres per second. Okay, so this question here, a lot of information, but draw a diagram, you'll be absolutely fine. Okay, let's go on to, is this the last page of questions? Oh yeah, so only 3 more questions. So 1.8, we've got a 5.2 gram ball, not that one, but this ball is dropped from 90 centimetres onto a surface. It bounces to a maximum height of 41 centimetres. Calculate the efficiency. So now for this one, we had this, I think, at the beginning. So I think this one here is 1.1e. And what we can say is that h1 is going to be equal to eta h naught. That means the efficiency is going to be the ratio between h1 and h naught. Okay. Now, it bounces up to 41 when originally it was dropped at 90. Now, these are both in centimetres, so the units would cancel, so I don't need to convert to metres for those. And if I work that out on my calculator, that's an efficiency equal to 0.4556 or 0.46, or indeed 46%. How fast would the ball in question 1.8 above rebound if it struck the surface at 2.5 metres per second? Well, again, I'm now going to use the equation looking to do with velocity and how that's related to the efficiency. So what we can say is that V1 is equal to the square root of eta V0. That's then going to be equal to the square root of 0.4555, the answer I had on my calculator. I'm not going to simplify it just yet. Multiplied by its initial speed, which is 2.5, and therefore that's equal to 1.687, so 1.7 metres per second. Okay. How high would a ball bounce if it struck a surface with an efficiency of 0.75 at 13 metres per second? So again, we know that the efficiency times its initial kinetic energy is going to be equal to the height it gets to, which is mgh1. Okay, so how high would it bounce if we know how quickly it was moving when it hit? Again, of course, the m's cancel. My pen is running out. We can rearrange that then to say that h1 is equal to eta v0 squared over 2g. Put the numbers in. So 0.75 efficiency times 13 metres per second squared divided by 2 times 9.81, and that gives 6.460, which is 6.5 metres. So that question there, again, it's a bit more tricky, I think, when you're looking at efficiencies, but there is nothing there that you cannot do if you've got a basis or a basic understanding of GCSE physics. There are no new equations there. We've got efficiency, we've got gravitational potential energy, we've got kinetic energy. The difficulty is the way that it's kind of often framed in the questions. Now, those were my work solutions to the first chapter. I'm not going to do it for the whole book because I don't have time, and also Isaac Physics don't want people just to be making solutions available for anybody to look at. So I'm not going to do that, but instead I would say, in conclusion, If you are thinking about doing physics or engineering at a high level, beyond kind of A level in the future, or even if you are just doing A level and you want to get the top grades and be assured that you're getting the high grades that you are capable of, then you can get this book. You can do everything in it completely for free. And if you learn to work independently through this, then I have no doubt that you're going to absolutely sail through any entrance exams for universities and also your years at university. And then I guess beyond that, when you're a real proper engineer, physics person, or just rich person in the city. So yeah, that is the Linking Concepts book from Isaac Physics.